Hello there, can you hear me at the back? Yes? Yes? Good. Start. Okay, so I'm here to talk to you about CSS4 Color. You're probably all using CSS3 Color, which is something I co-wrote. This stuff is a bit more cutting edge. It's new stuff, brand new stuff, actually. And the main problem I find when I explain it to people is they go, yeah, the syntax is fine, but what does it all mean? How do I use it? What can I do with this? So what I'm planning to tell you is all about CSS Color. So first of all, that's me. I've already been introduced. I work as a technical director at the World Wide Web Consortium, W3C. Tim Berners-Lee is my boss. I started SVG in the sense that I got the requirements document together, got the people together, convinced companies that they should be better working together and competing. And I was also the first chair of that group. I was a co-author of PNG. I was the chair of the group that did web at font face. I invented that. Also later on WAF1, WAF2, and most recently chromatic fonts. First chair of the CSS working group. CSS2 co-editor, and the most important thing, CSS4 co-editor, which is what I'm going to talk about today. This is Wooly the sheep, by the way. This is a CSS working group mascot. It came about because I kept on complaining that specification text was too woolly. Shave off the wool, get rid of the wool, so we ended up having a sheep as a mascot. Okay, what are we going to talk about today? First, I'm going to cover some basic things about light and color and stuff like that. Then we're going to talk about how can you measure color. CIE Lab. Does anyone know what that is already, by the way? Hands. A few. Nice. Okay. Lastly, well, about color displays. About CMYK. Anyone here also do print design and stuff like that as well as on the web? A few hands. Okay, good. So you know all about having colors that just look nothing like what you originally on the final run. And then lastly, the last little bit of the slide, and I will get to it, I promise, is actually what's in CSS4 Color. By the time I get there, you'll understand what it does, and you go, yeah, that's obvious. I hope. Okay, so who can tell me what is that? What is this object on the screen? A prism, yes. What does it do? It reflects light. What is the result of that? What happens when it does that? You can see a rainbow, that's right. Now, there's several very good points in there. You can see a rainbow. If a snake looks at it, or a bumblebee or something, it will see a different rainbow, because it will see bits of infrared. So humans are seeing the rainbow. They're seeing the different colors in that white light. Good. So there already we have our first definition. Light, for the purposes of this, is defined as those wavelengths which are visible to humans. We don't care about other animals or anything like that. What we're talking about here is humans, and humans have color vision. So here's a visible spectrum. Don't worry about the numbers. These are in nanometers. You don't have to know them. The important thing is that it's very bright in the middle where it's green, and it gradually fades out to the other colors, and basically fades off to black into the infrared and the ultraviolet. Okay, then as we said, it's human, so here is a human eye. Ignore all of that complicated stuff. The only part that we're concerned about here is the retina, which is the part at the back of the eyeball which accepts in light and gives you some sort of nervous signal. They are actually nerve cells, and they're connected directly to the brain. The retina is in fact part of the brain. And it has these things in them. The one on the left is called a rod. It's used when you're under like moonlight and stuff like that, and you can barely see, but you can still see something. And in particular, you have very little color vision there. And the other ones are called cones, because someone in a fit of fancy thought they looked vaguely conical, which honestly they don't. And I put 3 of them there because you have 3 different types in your eye. So here's a graph again of wavelength and the relative intensities of the 3 types of cone. Now, if you look at this, you can see the first thing that should strike you is that these all have very different sensitivities. One that's really sensitive, one that's moderately, and one barely at all. The next thing you'll notice is I've picked some interesting colors for them. Purple, yellowish green, and greenish yellow. This is to make sure that if you ever read in any other book or website about the red, green, and blue cones, you can tell that you're onto the wrong thing because they have nothing like that. Those are actually their peak sensitivities. And you can see that they overlap a lot. Now, if you were designing a system like that, someone would tell you to throw away and go better. You need less overlap. You're not going to be able to distinguish different colors with this system. Let's look at this again on a log scale, and we can see things a bit better. Yeah, these really do overlap a lot, don't they? And the purple-violet one, it's really not sensitive at all. It's a strange system. If you subtract rather than adding the different channels, though, you can start to discriminate. One of them is going to be showing much more at the red end, one more at the green end, and this is, in fact, the basis of our color vision. And lastly, we have the human brain. The pink bit at the back is where the visual cortex lies. So it's not, processing isn't finished by the time that the signal goes along your optic nerve into your brain. Much more happens there, all sorts of complicated things. Now, what I would like you to do, audience participation time, stare at this fixedly, look at the black dot in the middle, and keep staring, and I want to give you about 30 seconds to do that. Try not to let your eyes track away and look at different parts of the screen, just focus on that shape. I'm glad I have a little timer running here, because to me this seems like 30 seconds already, but it's only 15. Okay. Okay, what happened? Did you see a color? Yes, you can still see a color. Let's do that again with a different one. Same deal, 30 seconds. Yellow. Now, you already know about this stuff, right? You know it in terms of the names of colors. You can have a reddish yellow, okay? It's called orange. You can have a reddish blue. It's called purple. You can't have a reddish green. They're opponent colors. You can't have both of them at once. The two sensations are, you can't have them both at the same time. And similarly, you can't have a yellowish blue, but you can have a yellowish green. So you already know that there is this notion of opposing colors. Next example. Now, I took this. You've probably taken photographs like this by accident if you switched off auto white balance. This is a picture of a white piece of paper in my hotel room. And it's yellow on the picture. But when I look at it, it's white. And if I would take it outside into a sunny day and look at it, it would be white. But if I took a picture of it, it would be light blue. Our brain can adapt for things like this because this is information that the brain needs to filter out, right? When we're walking along, when we're sort of hunter-gatherers and we're trying to find out what's eating us and whether there's food around, we don't care whether the sun went behind a cloud. We still need to know that that's a tree and that's a rock and that's a jaguar. Okay, so our brain has got an awful lot of very careful processing to make sure that whatever it thinks is white remains white and all the other colors shift with it. We'll come back to this later because this is a very important point in terms of how we see color. And there's other practical things. If you don't have a good reference for white, your brain, all this processing power in your brain is trying to work out what's happening and will often get it wrong. If you crop in on that, you can convince yourself it's a blue dress or that it's a white dress or whatever it is. This is the entire basis for that. That's your brain going into overdrive trying to figure out what's wrong. So, color. Let's have a definition of it. It is a subjective sensation in the human brain caused by visual light acting on the human eye. Whoa. That's going to be difficult, isn't it? It's like measuring love or something. How can we ever do anything with color? It's just what? Okay, so how are we going to do this? Well, we're going to have to measure how much light is coming in at all the different wavelengths, and then we're going to have chemical analyses of our eyes and the retinal spectral sensitivities and all sorts of stuff, and the electrodes in the brain, and okay, we don't, actually. There's lots of things that are much simpler, so this is a very, very complicated system, parts of which are not well understood. We can measure it as a system, as an entirety. Okay, we can just say to a person, look at this color, is it the same as that color, this sort of thing. So let's see what we already know. How do we measure color? First thing we know is that brightness varies by wavelength. There are certain mid-green type colors which come up as very bright. We can see them very well, and the same with some yellows. As it gets off towards the red, as we saw in that spectrum earlier, as you get off towards the red and the violet ends, our sensitivity goes way down. There's two curves here. The other one is that moonlight sensing rods that I told you about, which has a different sensitivity. Don't worry about that, because that's nothing to do with color vision. Okay, so we've already got that. Now, can we imagine where this comes from? We've already seen a graph that looks sort of similar. If you imagine adding the two biggest peaks together, this is clearly where that's coming from. You've got two channels and they're being added together, and it's therefore not much of a surprise that the other thing you do with those two channels is you subtract them to get a color difference thing. And the other thing is, we've only got 3 cone types, and they overlap a lot, so effectively our brain has got 3 sources of information about what our color is, so we don't need an entire spectrum, actually. We can be fooled quite easily, and this brings us on to an important point. You can have 2 colors that look identical, and they can have wildly different spectra. I was actually trying to get a much better slide than this. This is my I give up slide, about 2 o'clock this morning when I thought I'm not going to find this data. But I have seen this. It was a spectrum of like a flower, a yellow flower, something like that. And then the spectrum of that same flower being displayed on an old cathode ray tube monitor. And it's spikes and it's all sorts of stuff in wildly different spectra, exactly the same yellow. Looks exactly the same. So because of the way that human brain and eye work together with only 3 different cone types, you only need 3 numbers to describe a color. Not like hundreds for all the different wavelengths, but just 3. So this is a useful simplification. How do we know this? There were some experiments done in the 1930s about color matching. And what they did was they took 3 lamps, which are at the top there. One of them was a deep red, and the other 2 were like a greenish yellow and a bluish violet. They use those because they use mercury discharge lamps, which have a very stable spectrum, and you can therefore get a color that you know precisely. All the different laboratories will have exactly the same color. So you've got 3 lamps, and you've got like 3 sliders or dials or something. You can adjust the sensitivity. And then on the other side of this screen, it's like a ground glass screen, you've got some random color, a random wavelength, and the test subject has to match it. Okay, so I mean, this is very similar. This is like a color pack here, except it was 1930s. Now you notice I've got the same 3 sets of lights on the other side, because it turns out there are some colors that you can't match. Right? You turn the red all the way down, and you need to turn it down more, below 0. You can't do that. But what you do is you add red to the other side until the 2 things do match, and then you consider that to be a negative amount. Okay, great. So now we can match any single wavelength right the way across the spectrum. We know how much of these 3 primaries are needed to make it. So that's great. We can fake colors. They look exactly the same. They're visually identical. But these negative numbers are terrible, especially in the 1930s when you're using logarithms and slide rules and stuff. So the first thing they did was transform that to a different system called CIE XY. CIE, by the way, stands for a French abbreviation, which means International Lighting Committee. So don't worry about that, that's what it means. XYZ has some interesting properties. Firstly, it has no negative numbers in it. All visible colors are a positive quantity. Second thing is, the Y part of XYZ is that luminous function we saw, the one with the sharp peak that tells us how bright something appears. So we've already got one channel that says how bright it is, and the other 2 contribute to that, and together they tell you what the color is. And thirdly, it has a property called additivity. What that means is you can do math with it. If I measure, say, one of those blue lights and measure its color, and then say there's an orange light over there and I measure its color, then I can predict if the lighting technicians move two lights onto me, what color the mixture will be. I can say I can do an average of those two, and I will actually get the result. And if I measure it, I will prove that in fact I did get the same result. So you can do lots of calculations with it. It's a very good space for doing calculations. It's a good space for doing compositing. Doing compositing in something like XYZ, which is a linear light color space, gives you much nicer results than doing it RGB. Okay, so XYZ is great. You can measure it. You can. By the way, when I say measure, I mean using something like this, which has a little lens, and you put it on somewhere, and it measures, and it gives you a readout that tells you what the XYZ values are. So these things exist. That's great. So we're all good now. What's the problem with it? Well, this is that's horrible. The bands are what's troubling me, which are not at all on my monitor. But what do you notice about this gradient? Is anything wrong with it? Apart from the lines are an artifact. The black's all bunched up to one side. It goes way too rapidly up to white and then is pretty much light all the way along. So that is luminance for you. Luminance is not what we call perceptually uniform. In other words, we see a lot of change at the beginning and not much change at the end. So XYZ does have some issues. It's not perceptually uniform. Also, white adaptation, it's very good if you want to measure what white is, right? You can have different types of white, like cool whites, warm whites, all this sort of thing. You can measure them, you can get numbers in XYZ that tell you what sort of white it is. But we already know that our eyes will basically then adapt to that. They'll shift it around so that we see white as white, always. So XYZ isn't super useful for that, which is why I'm now going to talk about CIE Lab, which is a much better color model for representing how we actually see colors. So first of all, it transforms the luminance channel into a lightness. And this is a graph of CIE lightness, and the important thing is that exactly at 50%, it's a mid-gray, not a light gray or dark gray, but it's in the middle. It should be even steps. It's actually better on my screen, but it's even steps all the way along. So that's the property of the lightness channel. And then we have two more called A and B. Oh, just to let you compare, right? That's lightness, that's luminance. Then we have these things called A and B. Now, again, sometimes in books you'll see A being described as red to green. Well, kind of, but not red and green like you would imagine them in RGB. They're sort of a pinkish color to a sort of teal. And on the other hand, we've got a mustard to a mid-blue. These are all at a value of L of 50. You get different colors above and below. And what I did was I put them into a calculator and converted them to sRGB. Notice the one on the end is transparent. What that means is that color can't be displayed in sRGB. It's too saturated, so I had to miss it out. So we've got now a color space which has a central lightness axis, which always goes from 0 to 100. And 100 is white, and 100 means the white that you're currently looking at, the white you're adapted to. So you'll always see it as white. And then we have these two color channels. So you can actually, this sort of instrument can measure things in LAB as well. Often you'll have graphic artists and whatever, they want to measure physical colors, they will get a readout in LAB. You can have a color picker or something in Photoshop, which will give you results in LAB. Has anyone here actually ever used LAB in Photoshop? Done anything with it? Yes, it's pretty cool. If you convert your image to LAB, which, by the way, you have to convert it to a higher bit depth first, otherwise you'll lose information. Convert it to LAB, select just the L channel, and now you can sharpen on just that one without introducing color artifacts. You can do, it's pretty useful. You can do things like that. So, okay, so this is great, But the A and the B, they're kind of, it's like trying to mix a color with RGB sliders. You're sort of fumbling around and you mix one and then you have to nudge the other one down a bit. It's not very good. But if you think about it, if you've got a rectangular coordinate system, you can convert that to a polar coordinate system where you have a hue angle and you have what's called chroma, which is kind of like saturation. The further out you go, the more saturated it is, the closer in you go, the more neutral it is. So there is a little color wheel for the CIE hue. Is this reminding anyone of anything? This idea of like hues that go around in a circle and yeah. HSL, yes, it does. One of those strange coincidences. This came out in 1976. And in 1978, someone that didn't know much about color science but thought that the idea of a hue angle was cool came up with some incredibly tortuous math and produced this color model, HSL, which does indeed have all the colors around. It does have a lightness thing. It does separate out the different visual parts quite well. You've got hue, you change the hue slider, hue changes. Unfortunately, it lies to you an awful lot. For example, it tells you that yellow and blue have exactly the same lightness, and guess what? They don't. But it does make it nice and regular, whereas if you were to do that diagram in LAB, then yellow would be up here and blue would be down there, so it would actually correspond with their visual and measured lightness. But it's a more complicated shape. But in general, LAB is a very good way to visualize colors in 3 dimensions, see various things, the relationship between colors. It's perceptually uniform, or fairly close to perceptually uniform. If you measure the distance between 2 colors, that tells you how similar or different they appear. And that's true regardless of where in the color space it is, so you can compare sets of colors. In fact, that's used in the printing industry. If they have a color proof, they'll measure it every so often, every few thousand sheets, and then they'll express that as a difference, a color difference between what it should be, what it actually is. Okay, great. So now let's get on to color displays. So what we have here is a different type of device which hangs in front of your screen and measures the color coming out from it. That's how you characterize your color. Characterization is the process of measuring just the colors produced. You can do red, green, and blue separately. That's fine. And what you measure is what is the actual gamma curve exactly. You measure all the different points and see what it is. And it'll be slightly different for the 3 primaries. So you measure them at various different intensities. And then based on that characterization data, you can now calibrate it. In other words, you can add correction factors so that the grays are always gray all the way along. You don't have a dark gray that's a little bit brownish and a light gray that's a little bit bluish and that sort of thing. And you have a known white point. You can correct it to the white point that, for example, you're trying to use on your print. So lastly, having done that, what you have is sort of a volume in LAB space which tells you the range of colors that this particular display can produce. Now, if any of do any of you use like high-resolution monitors with like Adobe RGB or something fancy like that? Anyone? A few, not very many. If you've ever thought about those, or more to the point, if you've ever thought about buying one and then you find they're a bit expensive, you'll see that the advertising has this sort of horseshoe-shaped diagram, and it says, look, it's got this much %, and it's all. Ignore those diagrams. Those are in XYZ space. They're not perceptually uniform, they're just going to lie to you. What you actually want is to see it in 3 dimensions in LAB, which looks like this. Okay, so here is a top-down view. The L-axis is pointing straight out at us, and the A and B axis, and this is sRGB. This is the range of colors that sRGB can produce. So it's a reasonable range. It was fairly well chosen, actually. It's actually the same range as HD television, which is where the primaries come from. Now, people often complain about sRGB and say that it doesn't cover all that you need for print, and it's really not very good. This is true, but there are worse ones. Not pointing fingers too much, but here's an example that I did actually measure. This is a MacBook Air. And if you compare that, well, it's quite a bit smaller. Quite a bit smaller. So there are devices that can't do all of sRGB. And there are devices that can do quite a bit more. So this one comes from the broadcast industry. This is what's called DCI P3, and it's used for 4K television, that sort of thing. It's a wide gamut. It's broadly equivalent in terms of its size and coverage to Adobe RGB. And it's interesting that recent Macs, high-end Macs, have DCI-P3 as their gamut. They can actually do all of those colors. And this is very good news because Apple came to the CSS working group and said, we're about to ship a bunch of devices that can do wide gamut stuff, and we want to send wide gamut images to them, so we need a media query for that. Can we have one, please? And people said, yeah, sure, you can have one of those. And I was very happy because that meant that maybe they'd be implementing something using color management, and that would be great. There's an even huger one, which unfortunately I didn't have the data for to make one of these. It's called 2020, and it's used for 8K television, experimentally. There are very, very few devices that can produce the full 2020 gamut. But basically, that's almost all the colors that humans can see. It's incredible, but also incredibly expensive at the moment to make. But as a target for things, it's useful. So there we are. Now you can see. So when people say how many range of colors it is, it's basically the volume of that space you want. You want a gamut volume, not some percentage done on a 2D chart, which is not uniform. Okay. Moving slightly on. CMYK. You can do calibrated color. In fact, it's much more common to do calibrated color in the print world because basically if you don't, your result is rubbish. Your result is unusable. Inks are a bit different from primaries on a screen. The colors mix, right? Like lights on a stage. You can have your red and your green and your blue. They mix together, produce a color. If you've got cyan and magenta and you overprint them, well, the inks aren't transparent. So the one that you printed last obscures the other one. And they bleed into each other and produce horrible muddy colors. So this sort of dot pattern is used. You have dots of different sizes to simulate, because printers have got very high spatial resolution, but they're not very good at laying down precise amounts of color. So you use a dot pattern to simulate it. And to stop them overlaying, that's why you have these different angles that the dot patterns are. You'll have seen this sort of rosette pattern that happens when they all start to crowd together. You'll have seen that if you walk past a billboard, which is designed to be viewed from 20 meters away, and if you walk right past it like this, you can see this pattern on it. So what do you do with a CMYK device, like a printer? Well, firstly, you measure the color. But not just 10 values of each of red, green, and blue. No, you need thousands of different patches, all the different possibilities. You measure them all, because they all interact. It's not an additive color space at all. So you measure a whole ton of them. You have a sort of chart like this, and you have an instrument like this. And if you're doing it actually for work rather than just for messing around as a hobby, then it's on a motorized thing, so it can measure it by itself, because there's thousands of these things to do. It take hours. And then you put that into some software which works out what the result. It does a calibration. So essentially, to use one of these, you have a color that you want. You look through all the patches to find the closest color, and then you find some other colors that are a bit less close, and you interpolate them. You do an inverse 4D interpolation to guess at what the correct values would be. And the result of doing that is, firstly, you get neutral grays. You don't get shifts. You don't get hue shifts in near neutrals, like skin tones and things like that, which is very important for the cosmetic industry. And you get accurate colors in general. You get the colors that you want. Blues do not suddenly turn into purple just because you printed. Now, having done all that measurement, you don't want to throw it away and have to do it again tomorrow. So it's written out into a thing called an ICC profile. ICC stands for the International Color Consortium. So they're the ones that characterize this. They were started off by Apple, and then other manufacturers joined them. So you can store the characterization data, and basically this is saying how I can go from this to LAB or to XYZ, either. It doesn't matter which one. And if you have two of those, say one for your monitor and one for your printer, then a color management software can go from your monitor to, excuse me, your monitor to XYZ or LAB, and then from there out to CMYK, and you can have the same color all the way through. So ICC profiles are important, and they're the general industry standard way to move this sort of color calibration data around. Are you with me so far? Are you seeing what the point of it is and what it does, or has everyone gone to sleep? No, we're good so far? We're good. So really the thing I want you to get to take away from this is that colors, although they're subjective things, they can be measured. And we know that it's the right answer because we can test it. We can say, is this the same color as that? Our math says it should be, and people say, yes, it is. It does match. Good. Now we're going to get on to actually the CSS part of the talk. Woohoo! So you know what LAB is for. What's LAB good for? LAB is good when you want to compare different colors and see how far apart they are. And LAB has got these A and B axes that are kind of annoying, so what you actually want is a polar form with a hue angle and a chroma or a saturation axis. Good. So, LAB in CSS Color 4. So here's some examples. The syntax is pretty much as you would expect. It's a functional notation, LAB, parens, 3 numbers. L, A, B. That's it. So if I have a device like this and I measure, I don't know, this tabletop, and it gives me a readout, I can just type that straight into my style sheet, and that's the color I want. Cool. The second example has a comma and then a percentage. That's the alpha value. So you can have alpha as well. And the third example not only has an alpha, which is 1 in this case, i.e. fully opaque. Notice, by the way, that I've got some decimal points in there. You're not restricted to integers. You can put floating point numbers in there. You can have them as precise as you want. The last one, hash F06, what does that look like? Yes, it's a fallback color. If you have a system that doesn't understand color management or whatever, or if, we'll see more examples later on where a fallback color will be much more useful. Sorry. Then a fallback color is handy. So you've got your LAB values, you've got your alpha, and then you've got a fallback color optionally. LCH, which is the one I actually suggest you use, much better. You've got a hue angle, you've got a lightness, a chroma, and a hue angle. So the last one is the hue angle. My apologies for all the coughing. Okay, ICC color. So I mentioned ICC profiles, and this is quite common in the print industry and somewhat common in high-end photography. So we have 2 ways to do this. If you want to use DCI P3, which is the big wide one that I showed you, you can use that directly. You can also use Rec 2020 if you really want to be ambitious. And so again, we have a color function where the first parameter is one of these reserved names, and then you have the values with an optional alpha. Here's an example where we're using an ICC profile. So we've got color, and the first thing is not a reserved word, but it's one we make up. We've got foo here. And then we have an at rule, which is like at font face. So we define the name foo to be this profile over here with a source thing, just like in at font face. Now, this is the sort of thing where a fallback color would be really useful because the ICC profile has to be downloaded. That might take some time, so you won't have a fallback, or indeed, the network might go down. So this is really where you should use a fallback color. Otherwise, you'll have the flash of uncalibrated color, which is a new thing. You haven't heard of it yet, but you will. So pick a good fallback, and then people won't really notice. Can you use it? No, you cannot. It is not in the browsers yet. Slight secret here, the first public working draft of this spec was published next Tuesday. I know that. Trust me, it will be there on Tuesday. So you'll be able to read about this. Meanwhile, there's an editor's draft, so you can actually read about it if you want. So this is interesting stuff. It's going to give the web world a bit of what print has taken for granted for like 2 decades. It will allow us to use the increasing numbers of high gamut devices. I mean, this phone, for example, this has got a DCI-P3 screen. You know, it's not just high-end stuff, and this laptop as well. And that's it, actually. That's it for me. Oh, I should say these, for some reason my slide has reformatted itself, but these slides are up on GitHub if you want to have a look.
So, thank you, SVG Jesus. We don't have a lot of questions, which I wonder why. It kind of brings me back to the days when I used to do print and design way back in the day. And I remember working in LAB because you could do things you couldn't do in other color spaces in Photoshop. And I had bought a book, Photoshop LAB, I don't know what the name of it was, but it was like 700 or 800 pages. And it was just only about Photoshop LAB. So that kind of connotates the immense amount of information there is about just one color space.
Right.
So in light of that, are there what are some good resources? Is there like a compendium or one good introductory thing?
Not really. I mean, there are various books about measuring color. The books tend to be aimed at the print industry mostly because they're the ones that actually need to use it. There are some books specifically aimed at Photoshop users, but they tend to be more, you know, screenshots of dialog boxes and that sort of thing. You can actually, if something's 800 pages, they're padding it out to give the heft so you don't feel bad about spending $80 when you buy it in the shop. But yeah, you can do a lot of, I mean, the thing about LAB is that the lightness and the colorfulness are entirely separated out. So you can affect one without affecting the other. And also, if you put it into XYZ, that means you can composite together. You'll have seen if you do anti-alias stuff in one color on a different color, you get sort of kind of color bleeding at the boundary, and that looks kind of ugly. If you do that in XYZ, you do not. It's just a clean, crisp division because you don't have that bleeding of color into the luminance channel and vice versa. And because it's an additive color space, which means that when you do math on those numbers, you actually get the right result, as opposed to our result, which maybe looks nice and maybe doesn't, and you don't know, and it's all kind of guesswork.
Right. Of course, Facilis, which color function would be best for generating random colors?
I would suggest using LCH, because then you've got a clear separation, you've got your hue, you've got your chroma. You can, so if you want to generate a bunch of neutrals, you would constrain the chroma to not be particularly high, or you might have a Gaussian function, so they're mostly neutral but go out like that. You can constrain it to particular areas of the hue angle, so you might have opponent colors or triads or whatever. So, I mean, random colors is sort of interesting, but using color theory to do opponents, split triads, all this sort of stuff, yeah, that's the other source. If you go to a book about color theory for artists, for painting, they have all of this. They've got the hue wheels. They've got how to do color harmony, all that sort of stuff. Directly applicable. It's the same human visual system. They're just approaching it from a pigment-based direction, but all the same stuff. So yes, actually, you could. I can imagine that you could have some sort of web tool where you pick a few colors and then it makes gradients of them, it makes things, and you can get a whole color scheme out of that. Desaturate the colors to reduce the background, that sort of thing. Doing calculations in LCH would be a very good thing to do. I should point out, for those of you who are interested in that sort of thing, that when the spec gets published, it includes a JavaScript function library, which I put together. No claims for a great code quality, but it does give you the right numbers. So if you want to convert between all of these, between LCH to LAB to XYZ to sRGB to whatever, the functions are all there. So if you want to write things that do, you know, palette generation or random colors or whatever, sure, have at.
Can I do that with radio,
Yes, absolutely. You just need 360 of them arranged in a circle.
I appreciate that knowledge. I just think that you're enabling him, really. What does new white balance technology like Apple's True Tone for the iPad Pro affect how we define color in our designs?
Someone will need to tell me what the True Tone does, and then I can tell you.
Ruben, where are you?
Yeah, so you gave the example of how light is different when you're outside.
Yes. Mm-hmm.
That's what they're actually adding to modern screens, well, actually from this year on. And I was just wondering,
Okay,
what
so
does it mean for us?
what I imagine it's doing therefore is it probably has a colorimeter. So you get screens which have a light sensor. Okay, it just measures luminance. And then what it'll do is increase the contrast as the light level goes up. And as the light level goes down, it'll bring down the light level of the monitor so it's not blinding you. So that's a simple and easy one. But instead of having just one light sensor, if you have multiple ones, then you can get an idea of the color. And you'll see this in photographic light meters. They measure the color temperature. So what I suspect they're doing is shifting the white balance of the screen so that actually the white that you see out in the environment and the white that the screen has are together. Because if you've got a bright window, I talked about this adaptive stimulus, the primary adaptive stimulus. If you've got a monitor that's dimly displaying white, which is what you want to see as white, and there's a big white window out there which is much brighter, your brain is going to lock onto that and say, that is white, and this screen looks wrong. Whereas if the monitor is actually measuring what the light level is, what the color temperature is of white light, and adapting, then that's great. That means the monitor can actually shift to what your brain currently thinks of as white. Then that should give you more consistent results. It will also give you an interesting opportunity to wear a fluorescent orange t-shirt right close up to the thing. Orange light reflects in, and then you get this horrible... Yeah, I have actually seen like professional color matchers that are doing stuff for really high-end printing, and they wear like complete black smocks, right? So that their clothing doesn't reflect on the monitor and put off their color balance. And there's another outlandish example. I've seen color graders in the film industry who are doing, because they've got material coming in from multiple different cameras and different types of things, different lenses which have slight color casts. And what they have to do, they have a buzzer goes off every 10 minutes. And they have to look up, and there's this illuminated gray thing, and they have to stare fixedly at one for a minute to basically reset their eyes, and then go back to doing work again.
Wow. So you've done lots of different work on CSS, and how did you decide to get into color, and what it seems like quite a bit of research to do.
It is a lot of research. How I got into this was before I was working at W3C, I was working at a computer graphics laboratory in Manchester in the UK, and I was researching training materials for use for training people about computer graphics. And I got very interested in the color topic, and I spent way more time than I should have done. So the thing that I wrote about geometry and matrices and whatever was kind of short, but the thing I wrote about color was huge. And it took me way longer than it should have done. I had a lot of fun. So when I came to W3C, I was like, whoa, yeah, we've got to have color. And in those days, Apple had the beginnings of a decent color management system. And Microsoft had a color management system, which was not decent, but they rapidly replaced it with one that worked pretty well. And Linux sort of caught up, so I was like, great, we've got all these, we can have color on the web now. But unfortunately, the browser guys were not super interested. And then shortly after that, we went to mobile, and all these mobile devices don't have color management on. And it's taken another 10 years for that to sort of come back. So I've been pushing on this, trying to get color. I mean, there was color like this in the SVG 1.1 spec, right? And it was implemented because it was Adobe and Corel and these sorts of graphics-based companies who did the first SVG implementations as plugins. And yeah, they had color management built in. You could bring in a tagged image, and you could match on it. But that all went away. I mean, we got lots of benefits going to the browser-based SVG implementations, right? We got good integration with CSS. We got much better than I wouldn't go back to plugins at all. But the fact that these were graphic professionals doing it meant they took certain things for granted, particularly as they were dealing with the print industry as well. So yeah, they did color management back then. It's been such a long uphill struggle. I was so happy when Apple, like, we're shipping all these wide gamut screens now, and they're going to be in everyone's hands, and then Samsung and whatever are all coming out with wide. I'm looking to see what the new MacBooks come out with, because they're kind of due, right? And it'll be interesting to see if they have wide gamut screens as well. I really think it's happening this time. It's happening on mobile and laptops and desktop all at the same time, so I really think we have a chance. Please.
And it means more expensive devices, right?
Well, the price is coming down. I mean, it used to be you would pay 10 times the price for a monitor that you could guarantee it would keep its color calibration for a whole week. And now it's just a little add-on thing, right? You can get a device that just measures emissive color, a colorimeter, for about $100. And if you're calibrating every week, and you can use it on multiple screens, and that's not really a very large expense. And I mean, I was amazed. This phone that I got, it's an S7 Edge, whatever. Nothing particularly great about that, but I noticed in the settings, I can switch between sRGB, Adobe RGB, and DCI-P3, and it's just, whoa, I can do this. It's great. And I mean, you've got really nice high-resolution screens with a wide gamut. There's a need for this, and the home television industry, the home cinema industry, and that sort of thing is also going for that. They want to have brighter colors. They want to be able to control the range of colors more precisely.
But arguably, most normal people don't have calibrators.
That's
so
right.
there
needs to be a
question
fallback.
about the is it really helpful to go LAB when you don't have those kind of calibrations?
So if over time, ever since sRGB has been brought out, devices have tended to go much more closely to sRGB as their default model. So it used to be that all the different monitors from all the different manufacturers were entirely wildly different. They had different gammas and everything. Nowadays, they tended to go to much the same one. If you get a cheap inkjet printer that costs like $80, the chances are it's not you don't send that printer CMYK data. You send it sRGB, and then it uses some internal engine and puts it out. But this is a sort of known state. So I think we're going to see, and we're seeing pretty good accuracy. The other thing I've seen is monitors that ship with a calibration certificate. So they're basically measured at the factory, because a robot can, put a thing and measure a bunch of stuff and say pass, fail, and this sort of thing, and you get a consistent experience out of the box. I think this stuff is coming. The price is coming down. The little devices, the little chips that measure the color, they're coming down in price. The electronics, little microprocessors to do it at a small. There are a couple of open source things now for doing screen calibration. Mm-hmm. Yeah, I mean, I think the price is coming down. And it's coming to the masses. The thing is, there is a cost to people who sell things which are color sensitive, cosmetics, clothing. Apparently, there's a huge amount of returns because people ordered something on a website. It comes back, it's a totally different color than what they expected. Or for makeup, fairly small changes like, well, I can't possibly wear this. It makes me look too orange, too red, too whatever. And they send it back. And there's a lot of cost to that. So there must be some sort of willingness to do a bit to get consistent color. I think we really need it.
Well, I agree. It was very fascinating. Thank you.
Thank you.
Yes,